my my work on this topic had to do, I used to work for the European Commission, like the European government, in all their research problems, research projects, programs in environment and climate.
Mm.
And the ultimate objective of these projects was to make sure that the European legislation is appropriate for the various places in Europe. Because the water directives for Denmark don't work in the Mediterranean area and so on. So during the development of a number of these projects, we had to install meteorological towers, sounding balloons, getting permission for flying instrumented aircraft and so on. The information came in that there was a perceived loss of summer storms around the Mediterranean, the Western Mediterranean basin. And I was assigned the project to look into it. What we found was that most of the Mediterranean, the Western Mediterranean, make a picture in your mind between Italy and Spain, France, and Northern Africa, used to be covered with marshes as far as 2,000 years ago. It's in the historical records during the Roman times. And at that time, it rained quite a bit, equivalent to about maybe 2 meters of rain, no, 2,000. Yeah, about 2,000 liters per square meter per year, while the precipitation actually is no more than 400 liters per square meter per year. And as people sort of filled in the marshes, the coastal marshes and lagoons and so on, the amount of water that is driven inland with the sea breeze goes down, and the frequency of the storms goes down. And in the last 50 years, what happens is that there was a very fast industrialization of the whole Mediterranean area with power plants and oil refineries and housing and so on. And of course, the storms are gone. We have a number of scientific papers published on that, including what happens after you kill the storms in one place, how you may alter the system and propagate the effects down the line, so you may end up having huge floods in other parts of Europe as a result of changing in one place. You have concatenated effects, and all that has been published. I can send you the papers. And that's how I got involved in this topic.
Okay.
In my previous training, I was, by training, I am an aeronautical engineer specialized in fluid mechanics. And I got a PhD in atmospheric physics at the University of Toronto. And afterwards, I joined the Canadian Meteorological Service for many years. I had a leave of absence until I retired. So for all intents and purposes, I was a Canadian meteorologist until a few years ago. That's it.
So when you were, yeah, cool, thanks. So when you were first asked about why the storms were disappearing, had people studied this effect before in other places, or how did you figure out it was the evapotranspiration that was causing the storm?
No, what we did was to use the data we had collected for a number of European projects. We were actually looking at the beginning for the dynamics of atmospheric pollutants. And in the Western Mediterranean basin, there were very high levels of ozone, tropospheric ozone, damaging the crops because the air masses recirculate vertically. They go up the coast, back over the sea, down, up the coast, just like a big cooking pot. Okay. It happens in a few other places. In the Sea of Japan is known to happen also, and also in the South China Sea. Sea surrounded by land, these things happen. Similar things happen also in the Great Lakes of Canada that I was in Canada for 16 years. And no, the comment was, can we explain it using the data we already had? So what we did was to calculate, because we had all the data, the volumes of air displaced by the sea breezes in summer, because the loss of the storms was in summer. The first thing we did was to disaggregate the precipitation components, which nobody had done before, but it was a traditional method from the Canadian Met Service. So we found that in our area, we have three main precipitation components: the large weather systems coming from the Atlantic, the regional weather systems with large, what the English used to call levanters, big, huge storms in the Mediterranean Sea that they are known to happen ever since the time of the Romans. And then we had the local cycle, which were the summer storms. They only happen basically in summer. So when we got our data, we found that they're very well confined volumes of air displaced by this sea breeze system every day in summer. And of course, if you know the moisture coming inland, and you know the amount of heating that the air sustains as it moves 80 kilometers inland from the coast to the top of the mountains surrounding the Western Mediterranean Sea, you realize that the air coming inland from the sea has a contents of 14 grams of water per kilogram of air. And it heats up about 16 degrees by the time it reaches 80 kilometers inland. And at that time, to condense, it requires 21 grams per kilogram of air, which it would get plenty of it in times past. But after you have cut all the forest, and now you have barren rock, and you have built along the coast, you don't get enough water vapor now to the top of the mountains. And of course, the storms don't develop. There is not enough moisture to compensate for the amount of heating the air sustains as it moves inland. This was first presented in San Diego, California, in the Medecos conferences in 1997. And the head of the US Forest Service at the time, a fellow called Miller, said, well, if what you say applies in California, we will have serious problems with forest fires in about 25 years. That was said in 1997. I can send you the publications and so on. So, because what happens is that you stop the storms are the link for precipitable water between the large systems and the regional systems. In summer, neither of those systems work, and you only have the summer storms, what is called also the small water cycle. Okay, that keeps the ground fresh and keeps enough moisture recirculating in the system to keep everything else going. If you get rid of the storms, the vegetation dries up, and then when you get a big torrential rain in the fall, winter, the soil eventually is washed out and the barren rock comes out. So you have a feedback loop that goes to increased drought. And then other things happen. But then the vegetation that you, I'm looking at myself, I don't know what happened. The vegetation that you had and helped stabilize the soil and bring the storms or keep the storms going disappears. It's prone to fires because it dries up. And then you get into a feedback cycle. And all this is what I was telling you, it has been published.
So let me just recap what you were saying. So you were saying that as the water comes in, the water vapor comes in from the ocean, it's not enough to actually create rain. So you need to add the evapotranspiration to it.
Well, but that is because that air coming in from the ocean, you know, the sea breeze is developed because there is differential heating during the day between the sea and the land in the coast.
Right.
That differential heating drives the sea breeze. But of course, at the same time, it contributes to heating up the air mass that comes in from the sea. And that added heat, what it makes is that the cloud condensation level starts going up. And if you overheat that air very much, because you get rid of the vegetation, or you have the barren rock, or you build up concrete and surfaces and so on, they add a lot of heat, but they don't add moisture.
Right.
Okay. In the old times, you had a certain amount of heating provided by surface vegetation and a certain amount of moisture added through the vegetation. The vegetation, when it's heated by the sun, it cools itself by evapotranspirating water. So the air that comes in from the sea to provide or to make the sea breeze, it gets heated, but it also gets more moisture, okay? And eventually it reaches a condensation point and you have a summer storm developing over the slopes sometime during the afternoon.
Right.
And that cycle would go on for almost every day. That kept the soil moist, and the following day, that moist soil would contribute to the vegetation transpiring and put the moisture in the atmosphere again. And what you see is the same amount of water going round and around and around for many days during the summer. You change the surface of the land use cover, and you immediately change that cycle. Our calculations show that as soon as you alter an area of about 6 miles by 6 miles, I mean 36 square miles, the precipitation downwind already is affected. And that has been in the Amazons. They also found out very quickly that as soon as they cut 10 by 10 kilometers, which is about that area, about 100 square kilometers, about 36 square miles, precipitation stopped over that area. Because in the tropic, in the rainforest, studies financed also by the European Commission found out that about 65% of the water that comes down during the rainy season in the typical summer downpour, right? In the tropics, you have this rainy season, you get these huge storms in the afternoon. 65% of that water is from the water that precipitated in the 3 previous days. Okay, so of the 2,000 liters per square meter per year that you get over the Amazon, approximately 65%, I mean 1,300 liters, is the water that the forest requires to keep recirculating, so that your net gain is the difference. The water that ends up in the rivers is the other 35%. Okay, you don't get 2,000 liters. Of those 2,000 liters, you need 13 to keep the system going, so that the river can capture 700. Do you get what I'm saying?
Yeah.
All that has been published and has been presented to the European Parliament many years ago now, more than 20 years ago. And but nobody pays much attention until you guys now are interested.
Right. So basically you're saying in Spain or in the Mediterranean, there's 2 main reasons why the rain got less. One is that there's less evapotranspiration because you have nature, paved over. And the second is that, and the second is that because you paved it over, now heats up more. And so then the water, you can't hold as much water vapor in the air. And so, I mean, you can hold more water vapor in the air, so it's less likely.
But you don't add it.
Right. Yeah. So
Okay,
there's two
they're
reasons.
both things happening at the same time. You get so much water per cubic meter of air coming in inland from the sea that would naturally, if you lift it up, it would naturally condense at around 700 meters high. And sometimes in the mountains, very close to the mountain, to the coast, during the summer, you see these snow cap, these cloud caps developing around 700 meters high. And people use that cloud bank to capture water from using fog traps. Okay, fog.
Is this true? Is this true happening, say, in the US or Canada?
It's
Like,
happening everywhere that you change the land use around any coast. The part of the water cycle that was driven directly by the sea breezes on that coast changes. It's
so
just
in the
thermodynamics,
US, say,
nothing magic.
so in the US West Coast, we would be losing rainfall as we pave
Yeah.
over the coastal
Yes,
cities.
yes, you have been losing rainfall, and that was a comment that this fellow from the Forest Service made in 1997 when I presented our results in San Diego.
Mm.
In 1997, said we're going to have similar problems in our area. You know, in larger areas, it takes a little bit longer. And in California, it's happening now. Not only you have lost the local precipitation in the summer afternoons, but of course the ground has dried up. People have built in the forest. Now the ground is much drier than it used to be before, and it becomes a fire trap. That did happen around the Mediterranean a few hundred years ago. And we still have serious problems with fires.
So you're saying that the fires, say, caused in California, in British Columbia, in Greece, in Spain, in Australia, all of this is to do with paving over the land, and so there's less ocean air
all
coming
is
in.
to do changing, not paving. Paving is one,
Right.
changing the soil, the land cover.
Mm-hmm.
Actually, in the first book prepared for the United Nations for climate change for the United Nations Conference in 1972, there was a book that was published by the Massachusetts Institute of Technology called Inadvertent Climate Modification. And they talk about two drivers for the climate change: the greenhouse gases that everybody is so concerned about. And the second leg was land use, land cover changes, because they alter the hydrological cycle immediately. You know, as soon as you get a forest and you cut a piece of forest or you build a road, something like that, the small water cycle is immediately changed by a little bit. And people say, well, it's too little. But it's not too little when you start adding and then another little bit more and a little bit more. And eventually you hit what is called a critical threshold or a tipping point. All right. And after you cross that point, your local precipitation disappears. And then you only have the largest scale precipitation. So your regional water cycle begins to be changed as soon as you change soil use, which includes forests and soil, you know, the land cover. Land cover is the driver of the second leg of climate change. But because it's very inconvenient, you know, it's, how did Al Gore call the climate change the inconvenient truth or something like that? Right. You know, people focus on CO2 because it's very elusive. You know, one of the largest drivers of climate change right now is water vapor in the atmosphere. You know, the contrails of the aircraft emit radiation in the infrared, which is directly absorbed by water and ice, and you melt the mountain glaciers from within, because they will absorb all that radiation, infrared radiation, trapped by the water release in the stratosphere. And that will, you know, the surprise is they say glaciers are melting at -20 degrees centigrade, you know, but they're melting from within because the ice molecule is water and it receives the infrared radiation emitted by the water molecule as water vapor in the stratosphere. And that is a very large component of climate change that nobody says anything about. It was mentioned at the very beginning, back in the 1970s, by people from NOAA and NASA. They used to say, well, you know, you're focusing only on CO2, but you're not focusing on the water vapor. And the water vapor is about some 67 times stronger molecule per molecule than CO2. But of course, that means having problems with aviation and a number of other things that people don't want to hear about.
Mm. So what happens is that there's less rain, and then that will lead to more fire. And then you're also saying,
well, less rain means more drought.
More drought.
More drought means the vegetation dries up, and dry vegetation becomes fire prone.
Yeah. And then you're also saying it also led to more storms, like more bigger storms, right, in the Mediterranean. Is that true?
No, but not the local storms. What it means is that whenever you have a big downpour in another time of the year, it will make mud flows. The storms now, they hit a very weakened vegetation soil interface, and it washes out the soil. You get mud flows.
Mm-hmm.
That's part of the degeneration cycle that you trigger when you alter the land surface, land cover surface. You lose the local storms, and you're open to more damage by the larger weather systems. And eventually what happens is you end up, if you go to Southern Europe and you look around in Italy, France, and so on, the mountains are just rock, okay? And yet it is known from historical times that they were covered with forests no more than about 400 or 500 years ago. All that soil is now down in the marshes that people have built on that flooded soil. So now you have the coastline is filled up with cement and asphalt and houses, and the mountains are now barren rock. So the local storms are now gone, and something else is happening at larger scales. I mean, you don't, when you alter one place, you propagate the perturbations to larger scale with a delay of weeks or months or years. That is all explained in my paper in the Journal of Hydrology that I prepared for the European Commission.
So yeah, so I have a question. You're saying also that when I was reading the paper and I didn't fully understand, is that the air when it flows back up, it forms layers of water vapor, and it kind of, as it goes inland, it kind of goes up, and then it forms a layer, and then it can go further inland and forms multiple layers of water vapor in the atmosphere.
It goes the following way. When you have the system okay, you get air comes in, goes up the mountain, eventually hit the condensation level, you have a storm, you precipitate about the same amount of water that you have collected, and the rest goes into the upper atmosphere about 10, 12 kilometers high, it goes somewhere else. If you don't have enough moisture to trigger the storm, then the air that goes to the top of the mountain comes back in the return flows over the sea. But that happens because you have not had the storm. If the storm was there, there would be no layers forming. Okay? Layers form as a result of having lost the local storms.
And just to clarify, is there anything?
What paper are you talking about? The one in the Journal of Hydrology?
Oh, I don't remember which paper I was looking at. But I was just, so you were saying, how come the different layers don't mix? Is there like air pollution that's forcing them to stay?
No, because if the
apart,
layers
what's the reason that
inversion,
different layers?
inversions, and that blocks the mixing. They do mix through a more complicated process that is called a Margulis type 2 circulation that people work in thermodynamics, but is not included in meteorological models. Okay, so the layers are called layers because they have temperature inversions that avoids mixing between the layers on top and in the bottom. So you accumulate all that moist air in layers, and when it reaches a certain depth, it becomes what is called in meteorology potentially unstable. I mean, it's like a big cauldron full of boiling water that is expecting something to kick the pot. So all that can happen is that every so many days, a pool of cold air aloft, say above 5,000 meters, move from the higher latitudes and acts like a trigger mechanism. It just explodes.
So by temperature inversion, just to clarify for people listening, it's like
It's
hotter higher up than lower down, and so the air doesn't want to keep rising. That's the reason. So the water vapor won't keep rising and mixed with the water vapor above it. Is that the main reason you have layers of water vapor?
No. The air will rise depending on its temperature. Okay, let's go back to point 0 again.
Okay.
You bring in moist air from the sea. It is heated up and it picks up some additional moisture. And if the conditions are right, a storm is triggered. You get 1/3 of the accumulated water precipitates to the ground. That's the maximum that the storm will precipitate. The other non-precipitated water vapor goes into a storm cloud. You probably have seen them with a big anvil on top at 12, 13 some kilometers. And that water goes into the general atmospheric circulation. Okay. Now, the same air mass, if it's approaching the mountains but has not collected enough water vapor to compensate for the amount of heating, it will go up a little bit on top of the mountain, but doesn't go high enough because it doesn't condense. And then when it reaches what is called its thermodynamical equilibrium, it returns back to the sea. I mean, the air goes inland near the surface and goes back at different heights, depending how far inland you have created that chimney. You know, the sea breeze comes inland and creates one chimney, the first mountain range. If it triggers a storm, the process ends there. But if there is no storm, the air will keep going farther inland, looking for a higher point. If you trigger the storm, stops there. But if you don't trigger the storm, in our particular place, there are 4 main layers forming during the day. In some places, you only form one big layer because it depends on the lay of the land, you know, going from the coast to the inland. But in any particular case, if you accumulate enough moisture to compensate for the heating and you're able to trigger a storm, then the cycle is the normal cycle. That's the local cycle, and some of the water is returned to the ground and some of the water vapor goes somewhere else.
So if you have 4 layers of water vapor, when you trigger a storm, is the storm bigger? Do you have bigger rains?
Returns to the surface about the same amount of water that you have added along the path from the sea to the top of the mountain. You don't create any water. All you do is that you put the water on the sea breeze. If you trigger a storm, you get that water back. And then
is the storms bigger than a normal storm because you have 4 layers of water vapor? So is that more water vapor than normal?
No. It's a storm. There are no 4 layers of water vapor.
Okay.
The 4 layers of water vapor and pollutants occur because there was no storm. The air just gains certain potential temperature. And that occurs when there are no storms. Because if you trigger a storm, then a huge explosion takes place. Some of the water precipitates to the surface, approximately the same amount of water that you have collected along the ground. And you go from an open storm that used to be the classical or the old way, you go into forming layers over the sea because the storms have not developed. And they have not developed because you have added too much heat by changing the surface, and you have not added enough water for the largest storm to develop. I don't know if you...
Okay, cool.
It's not the easiest thing to explain, but anyway.
Okay, cool. So you're saying there's mainly two trigger points. There's the first trigger point is when you stop the rains, and the second trigger point is when you wash away a lot of the soil. So
Right.
if we're and this has been happening, I guess, all around the world. So if we had to restore,
all around the world, yes.
Yeah. So if we have to restore, is the first thing we have to do first restore the soil and then restore the rain? Is there an order we want to do the restoration?
Yeah, the idea is to restore what is called the small water cycle.
Mm-hmm.
It has happened in China. I don't know. Have you seen the presentations by John Liu?
Yeah. Uh-huh.
In the Les Plateau in China?
Yeah.
Okay, they reforested the desert, and now they have back the summer precipitation that had disappeared for 2,000 years. Once you recover the vegetation, a certain area of vegetation, you can recover the storm again. So that means an investment that humankind has never done. Humankind goes and gets and uses, but they don't normally think in terms of reinvesting. If you change anything in the watershed, you change the precipitation regime within that same watershed. That's basically what we discovered. And it can be recovered, but means an investment. You know, going and getting the trees from the forest and so on is what has been done usually, but nobody thought of replanting the trees because, you know, they take 25, 30, 50 years to come back. It's much easier to get than to reforest.
So if we were to say on the West Coast, or in California, we were to plant more trees, would that increase the rain right above the trees, or would that increase the rain further inland?
It would normally increase the precipitation at the headwaters.
So I saw in the musicology podcast you did with Tim that you were saying that in California it's important for the fog because it's the fog that we've stopped a lot of the fog rolling in, and that fog is hydrating a lot of our trees, right? So if we plant, would you say in order to stop, say, the fires that are happening in California, it's more important to bring back the fog or bring back the rain, or both? We can do it at the same time.
They're both. They're both. I mean, both contribute. Mm-hmm. But the point is that if you're building on those slopes, you're changing the local water cycle. Just as simple as that. But people don't want to hear that. Okay.
So we could say that part of the reason that there's a lot of fires in California is just from paving over the land and changing the soil use. And so in some ways, to if we want to have less fires, we have to like rewild a bit, you know, our state.
Yeah,
right?
You don't get nothing. You don't get anything at no cost. What happened in California, I was in the States when I was a foreign exchange student in Michigan in the 1959, 1960. California was then a dream place, okay? So that people were attracted to it and they started moving there in the 60s. At that time, I was living in Toronto, in Canada. And a few years later, when I started working on these laws of summer storms, I remember that changing the soil had already been accounted for in the first book on climate change prepared for the United Nations in 1972. I mean, it's nothing new, but people didn't want to listen. Do you hear what I said? I mean,
yeah. Wait, did they know about the small water cycle back in 1972 and the moisture cycling, this thing? Was that known back then yet?
it was known, but nobody paid any attention. And of course, there are a lot of people who will just oppose what you say. Oh, that's bullshit. You know, the system is too big. You change the soil, nothing happens. What can human do to the large planet? Well, they can screw it very well. Okay, that's the answer, because all the deserts in Mesopotamia, in Egypt, many of those places, they were forested places just 3,000 years ago. Once you start, there were marshes there. People start soiling the marshes to build up things and cutting the big trees to roll the stones to make the huge palaces. You know, you hear the comment, these people built palaces in the desert. That's just plain bullshit. People don't build palaces in the desert. To build a palace, you need big logs to roll the stones, or in the pyramids and so on. So that means when you get rid of those forests, the rain goes. Okay, so what the Mesopotamians did, they invented a rain god and they made human sacrifices. And a similar thing happens in Mexico. The civilization disappeared, and then eventually Mother Nature recovered itself, like happened now in Yucatan. Examples of human civilizations, including the Chinese one, that they destroy the system, the water cycle went to pot, and then they have to move somewhere else. But the contribution by the Chinese government in the reclamation of the Les Plateau, it has proven that you can get back the water cycle, the local and regional water cycle. Okay. So it can be done.
Cool. What I wanted to ask about, you know, with fires in California, like we have these things called the Santa Ana winds, these huge, hot, dry winds, and I think in different, I guess they're called fern. Yes. Fern.
They have been
Europe
there
or something. Yeah. So is our land use also creating these winds, or what's the role of what's the wind impact of land use on creating these hot winds?
No, those high winds, they're called in Europe, they're called foehn winds, Santa Ana winds, and so on. They normally occur when you have a frontal system coming from the other side of the mountain. So it would precipitate in the windward part of the mountain, and you have this dry, gusty wind in the lee side of the mountain. Those winds have been there all the time. The difference is now they hit very dry vegetation. So the vegetation has lost its natural protection that it used to get from the fog banks and from the small afternoon precipitations before they changed too much the land use. So the problem was there. The big storms in the Mediterranean were known in time of the Romans, but the problem is that they were not as frequent as they are now, okay? And those high, hot, gusty winds, they always were there, but they were not as dangerous as they would be now when the local cycle has disappeared and the vegetation is now unprotected.
Where the Santa Anas come from in California, it's dried up because LA has taken the water away from Owens Valley, and so that area has become desertified. So that makes those winds more dry,
those
right?
winds do not pick up the moisture that they used to pick up in old times, right?
Okay, so when we bring back the wetlands, that would make the winds a little bit less dry, and so then they would create less wildfire risk.
That's right.
Okay, cool.
That's right.
It seems like these days we have bigger and bigger atmospheric rivers dumping water on. And what's the reason for that?
Atmospheric rivers is a kind of term that has been invented by a group of people working in atmospheric physics to reword concepts that were classical in meteorology, okay? When you have a frontal system, the water is uplifted in one area until it precipitates somewhere else. If they want to call it an atmospheric river, that's their choice, but to me, it's just nothing. The same, what happens is that if you lose the local and the regional cycle of water, where you just recirculated water, that water ends somewhere else, okay? So the amount of water that you now evaporate from the Atlantic or from the Pacific is probably now more intense. The atmospheric river now carries more water than it used to carry in the older times. But it's not anything new. That was there all the time. It's just that they like to call it by a different name.
There's more of a temperature difference between land and sea these days. Is that causing more water to be evaporated from the ocean and then passed into the land?
Well, for that you need to increase the temperature of the water. But remember, that was one of the greenhouse effects that is never considered, because all the water vapor that you put in the atmosphere, whether it was in the soils or by high altitude aircraft, emits radiation that is absorbed by the oceans. So the oceans are being heated up, not because of the CO2, but because of the H2O. And that is one factor that people ignore systematically. You know, all the water vapor that you put in the extra, that you put in the atmosphere, acts like a greenhouse gas and is 100% more efficient in heating up the oceans or melting the ice caps or the glaciers than is the CO2. But it's this topic that people just don't mention. You know, for some reason, it's an inconvenient truth.
And why is there more water vapor above the oceans right now?
Well, because of increased aircraft, you know, traveling by planes, and also because a lot of that water used to be in the soils in historical times. Remember, before you had barren rock in many places and deserts in the world, there were soils in Mesopotamia and Chaldea and so on. There were big lagoons and marshes where now is just sand. That water is somewhere else. There is a group in Slovakia that had a little book called the New Water Paradigm. This book.
Yeah, I know.
That they estimate that 2 centimeters of the sea level rise that took place before all this boulaboo of the climate change correspond to the water that used to be in the marshes and the soils, in the forests and so on before humankind destroyed them all. Because that water vapor, if it doesn't go into the little storm cycle, it goes somewhere else. And eventually it ends up in the seas.
So we have runoff. So because we have more runoff from the land, we have more sea level rise. But why would the sea level rise lead to more water vapor in the air? Because it's evaporating more from the sea?
Yeah, there is more evaporation and it feedbacks onto itself. Remember, water vapor is 67 times stronger greenhouse than the famous CO2. Okay, that is something that should be engraved on people because they keep talking only about CO2. But any time that you disturb the hydrological cycle, you're creating a real monster. And the real monster is the water vapor in the atmosphere because it emits and absorbs radiation at exactly the same wavelengths than ice and water, liquid water. Okay, CO2 traps radiation that has to heat the soil and the soil then heat something else. But in the case of water vapor, you don't need any intermediary. You know, it goes directly from water vapor to liquid water to ice immediately. You know, is the radiation, infrared radiation bands. It makes like a perfect microwave in the atmosphere. You know, the microwave in your kitchen works at the wavelengths, that radiation wavelengths, where the water vapor in the food, the water in the food will be warmed up. That's why you heat up the water, but you don't heat the clay cup. But that is happening in the atmosphere. We're running that tremendous experiment with contrails, you know, from aviation, changing the water cycle in the soil so that you end up with more evaporation over the seas. And that water vapor is 60 times stronger than CO2. And it goes directly. You know, the argument that the glaciers in the mountains are melting when the outside temperature has not increased yet, it will give you the hint that that ice is now absorbing directly the infrared radiation now coming from the atmosphere through the water vapor in the atmosphere, whether in the lower atmosphere and the upper atmosphere. Because the water vapor can be liquid, solid, or gas, condensed or not condensed. It's very difficult to include in the climate models. So the climate modelers, they ignore systematically the water vapor and they only look at the CO2. You know, they're bullshitting themselves real good, but we'll find out.
Yeah, so one of the ways that there's more water vapor in the air is if it's hotter, because the hot air can hold more water vapor. But if we chop down our forests, then there's less evaporative cooling, so that our forests can hold less.
The point.
So the air can hold less. Then the air will hold more water vapor. So then that will have more greenhouse effects. So yeah. So in a way, the land use is creating more greenhouse effects.
Yeah. When you had forests and soils, you had a huge amount of water trapped in the soils and the forests that now you have freed into the atmosphere. So the idea, and that had an equilibrium that was equilibrium, say, of 70 years ago. As we have changed land use, we have perturbed all the water that was in the soils, in the forest, and is now elsewhere, including the atmosphere, where it can have a runoff effect as a greenhouse gas. So what you would like to do is make sure that that water vapor goes back to what it was 70, 100 years ago, or even better, to what it was a few hundred years ago, you know, before they deforested all the places in Africa and Asia and now in the States. You know, all that water is now somewhere else, behaving as a nasty component. Okay, it's not, you just don't change it and nothing happens.
Right.
Something happens, you know. Okay. That's the point.
So you said you looked at my water guidelines or water principles, and you said you agreed, just in a different order. Could you talk a little bit more about that?
Well, I don't have them on site, but basically the idea is that some of them are linked. I mean, the forest and the soils, if you don't have good soils, you don't have good forests. So they're all there together. And the soil behaves like a sponge that stores the water. Some of that water goes into the aquifer, which is another reservoir. In many places, people are digging into the aquifer, and water that had been down there maybe for thousands of years eventually ends up in the atmosphere again, and also in the oceans. You know, the people just look at the resource and they don't realize that that resource was recharged at one time when the system was working for itself. Soils, sponge, some water goes into the ground, some water goes into the vegetation, from the vegetation goes into the atmosphere, that goes into the summer storm, that goes back into the soil. Okay, and you have a huge amount of water doing a local job. And similarly at the larger scale, as soon as you alter all that, and some of that water fed the aquifers and so on, people just keep using water without realizing it, that eventually that water ends up where it shouldn't be. and it's a much stronger greenhouse gas than CO2.
Right. Let me I'm just trying to bring up what I wrote about so I just, which one are you referring to? So I wrote, so there's the water principles.
The best thing for me is to download it and I can mail it back to you with short answers.
Okay, cool. Yeah, because
because the point is that the main components are all there.
Okay.
But you, for instance, you cannot separate soil from forests normally, because a good forest is sustained by good soil. And if you if you change the soil use, you're changing automatically the forest and the water cycle. And whatever perturbation you introduce at even, doesn't matter how small scale is, it will only add up or amplify or propagate to the larger scales.
Yeah, let me just read real quickly, just the ones I said. So there was one was the more runoff, the drier the land becomes and the more fire there is. Two,
no, but the more runoff only if the soil is weak, because when you have a good healthy soil with a sponge that can accumulate almost half its volume in water, you know, if the soil is healthy, it can store a lot of water and there are less possibilities of having runoff. You increase the runoff when the soil has become weak because you have interrupted the smaller cycle. The soil gets damaged, the sponge dries up, it cannot store the water, and if you have a large storm, eventually gets rid of the soil altogether, and you have a mud flow, like you're having in California now. In California now they have mud flows because the soil up the slopes is not as strongly linked to the bedrock as it was in older times when you had the fog banks and the precipitation in the afternoons.
So really, to kind of like one of the key things we really should be focusing around the world in order to deal with droughts, fires, and floods is really just to increase the soil health, like to improve the soil health.
Yeah.
And what are the best ways? What are the best ways to improve soil health?
Yeah, I think you have something written that the soils are the best water reservoirs and you have.
Right.
Yeah, that's perfectly right. Okay, that's a transient reservoir that puts water in the atmosphere for redoing the cycle and puts water in the aquifer for eventually the aquifer also drains somewhere near the coastline or whatever and contributes to vegetation there or to marshes. All the marshes around the Mediterranean Sea were fed by the aquifers coming from the mountains. In fact, one of the problems I have when you cover those marshes with soil and you make houses in them is that the soil is unstable because that part is still getting water from somewhere that has nowhere to go, okay? At one time it would go into the marsh, and when the sea breeze came in, it evaporated a lot of water from the marsh. And the marshes had a fantastic evaporation mechanism. You know, you had willows and you had canes that dig, the wind just drops them in the water, lifts them up, dries them, lifts them up. So the evapotranspiration of a marsh with reeds is an order of magnitude higher than water just by itself. Okay, so all those little factors play and people tend to ignore them. That's what the problem is.
Right. So with this water principles, my idea is to kind of like say like the laws of thermodynamics, there's like 3 laws of thermodynamics. We can kind of put it into a very simple story, like a couple of laws or a couple of principles of the water, so that we can tell the story more simply, like the greenhouse effect or something. And so so I've been playing with multiple ways of doing these principles. And one of the ways I was thinking is that there's 2 basic cycles we want to do. One is the small water cycle, get that going. And the other cycle is we want to get building the soil. So basically, the more plants you grow, the more, then when they decay, you have the decomposers, the you know,
The
snail,
small water cycle and the
and
soil is
cycle.
part of the same cycle.
Yeah. So
That's
also
what
the
I
linking,
said.
yeah, the
Yeah.
linking of those two cycles is the key thing to understand. So maybe that's one way to present the water principles, like kind of, if we want to regenerate our, we want to eco-restore our lands and eco-restore our climate, then we need to
I can.
build, oh, if we
Yeah,
want
no,
to,
no, let me, I prepare a document for the, again, for the European Commission, called thematic issue, that is called Soils and Water, a larger scale perspective. You have much better reception where you are outside your house, wherever it is. I'll send it to you too, because the argument was that, and the problem, you know what it is that the British had large pasture lands. For some reason now the cows are not as profitable as they used to be before, and they're changing the land use. And in a place where never in historical times had floods or had mud flows, now they're beginning to get them. Okay, it's like they don't listen to what has happened somewhere else before. In my scientific world, what I notice is that it doesn't matter how many times people have explained and published certain things, no people will come up and they'll make the same mistake again. In the Mediterranean, another mistake they have made, they make all these maritime sidewalks along the beach. So when you get a big temporal, a big storm, the sand is gone and the walkway is exposed directly to the sea. The Americans learned that 200 years ago during the Civil War. They realized that you make construction or you put light towers close to the sea, and the sea hits a hard surface. It bounces back and takes the sand away. You don't find a beach underneath a rock coast. Okay, the enraged sea has to die off in a sand dune. So as soon the Americans discovered that you have to build behind the sand dune in order not to lose your beaches. They learned that in the Carolinas, in all those places. It is known, it was reported by the Army Corps of Engineers 150 years ago. And yet in Europe, they're making the same mistakes now, just because they don't read any of the information that is already available. Okay. And along my professional life, I realized that a lot of that information is available. I had an argument in one of the United Nations meetings with people from Israel when I was describing the sea breezes in the Mediterranean and how strong they were at one time or another, and they doubted. I gave them the report we had written for the European Commission, and the following day they told me, oh, we read through it and maybe you're right. And there was a large, tall guy with a big mustache that said, of course he's right. Who are you? Well, I'm the head of the Egyptian Meteorological Service. And they asked him, how do you know he is right? He said, and how do you think the old Egyptians could sail their boats against the Nile current? They waited for the morning for the big, strong sea breeze to develop, and they could sail up against the current. So the information was there for more than 3,000 years, but nobody used it. Or is reinvented time and time again.
Speaking of Egypt, do you think there's some efforts that John Lill and others are trying to do to kind of re-green the desert? Yeah, the Sinai. Is that
I was
possible?
talking to them just before I talked to you now.
Oh, really?
Yeah.
And you think that's possible to re-green the Sinai?
Yes, that was covered with forest in biblical times, and you could bring them back. Of course, means a large investment. But it's the same thing that has been done in China. You know, the movie by John Liu, you know, they have now reforested an area larger than France. and the local hydrological cycle has come back.
So, okay, so in the Sinai, so if we think of this as there's two cycles we need to restore, the small water cycle and also the soil cycle. So in the Sinai, do they first bring back the soil, or do they first try to bring back the water? Which do you do first to restore the cycle? Both at the same time?
Don't separate them.
Right.
You have
Okay.
to do both. And for a while, for a period of time, you'll be wasting water to maintain the forest going like they did in China. In China, they planted the trees, and in some of the pictures that I get from John Liu, you can see the first thing they did in China was all the gorges, you understand what I mean? The big canyons, they make reservoirs so that the water would stop and avoid the floods downstream. But that water was used to irrigate the trees they were planting until the tree becomes large enough and the soil underneath the tree is large enough, the soil, that becomes a sponge, and then the tree maintains itself for the whole year. And right after that point, the tree can then take from the soil some water, add it to the breeze, and trigger the storm. And then you recover the small hydrological cycle.
So you're saying it takes 10 or 20 years in order to get to that stage? Is that
well,
right?
in China, they got it in less than 15 years.
Uh-huh.
Okay. If you look at the data from John Liu, and John Liu told me many times that he's now sorry that he didn't get more pictures in the early stages. But of course, nobody was expecting to recover the hydrological cycle. Their interest was to avoid floods and to stabilize the dust storms and so on, and also move people to the regional areas, to the local areas, to avoid population problems in Beijing. Okay, the water came as an added, and it was the first time I talked to John Liu, we began to argue, and we realized that I was talking about how you lose the precipitation, and he was talking about he had documented that you can recover the precipitation by reforesting. But for a while you had to work, there is an expression that is called work like a Chinese, because they work very hard, and you can see that in his movies, how people work their asses off until the system was recovered.
Right. So I mean, in certain places around the world, the humidity levels is way below the dew point, right? So you need to increase a lot more the humidity before you get the rains back. So
you have to increase it at the proper place.
Mm-hmm.
Because the Chinese have done experiments in Africa where they reforested, getting water from the underground, for the water, how do you call it? Jesus, the word, from the aquifer. And they have lost the trees and the aquifer. The point is that you have to calculate for each watershed how much comes in, how much the soil vegetation contributes, and how much you need to recover the small water cycle at the head of the watershed to get back the summer storm. And then you get the system going back again.
Okay.
And that can be calculated. But going and reforesting like that and getting the water from the aquifer, you run the risk that if you haven't done your numbers properly, you're just exhausting your resource and you eventually get nothing back.